So let's take a look at postulate 2, Born's rule. It says the wave function is a probability amplitude. It's got a phase factor in it. So if we take the absolute square of it, we'll end up getting a probability distribution. So now we can see why we want the wave function and its square. So let's remind ourselves a little bit more about the properties of the wave function, right? The wave function is a probability amplitude. Being a probability amplitude is a sign quantity, and that allows for interference effects. But if we take the absolute square, we're going to get a probability density. Now, the absolute square is taken by the product of the complex conjugate with the function itself, right? And then we integrate over some region of space, and then we'll get the probability of finding a particle in that region of space. Now we bring in, to make unique solutions for our system, we bring in this quality known as normalizability. That is, if there's one particle in a state, then if we look over all space where that state could be, we better have one particle, right? That's what the normalization factor is about. Also, we'll find that whenever we have wave functions that describe a system, like the hydrogen atom, then all of the states of the system are described by different wave functions, and any two of those wave functions, they're orthogonal. There's no net overlap. That is, when we take an integral over the product of two wave functions and integrate it over all space, two different solutions of the Schrödinger equation, we'll find two different wave functions that describe our system will always be orthogonal. This integral will be equal to 0. Now, the wave function also is important. If we go back to postulate 5, the unitarity postulate, it says that for every physical system, there corresponds a unique operator representing the total energy of the system. This is so important as an operator that we'll give it a special name, the Hamiltonian, and the observable physical states of the system are described by those wave functions that satisfy the time-dependent Schrödinger equation. Oh, there it is. The simple case is that of a free particle. Free particle, no potential energy in this system, and its wave function is given here. Psi of spatial coordinates and time coordinates is just a normalization constant times an exponential function, I, times the quantity k, x minus omega t. K is the wave vector, omega is the angular frequency. Now, that's an odd way to describe a particle in terms of wave vector and angular frequency, but we can put it in terms of more familiar quantities by using, the de Broglie formula. De Broglie formula related the linear momentum to wavelength, which for a free particle we'll find is equal to k times h bar. We can also use the Planck-Einstein relationship of quantization of photon energy, right? That the energy is related to h bar omega. So let's substitute these two in here so that we get a new version of the wave function of a free particle. Rather than being in terms of a wave vector and angular frequency, we can get it in terms of, the wave function now is expressed in terms of the linear momentum and the total energy of the system. Those are two properties that we would associate with particles, so this is the natural way to express the wave function for a free particle. Remember, as always, for all systems, the total energy is kinetic energy plus the potential energy. But right now we have a free particle, so the potential energy is equal to 0. Therefore, the total energy is just the kinetic energy. So this time-dependent wave function, capital Psi of x and t, it is the solution to the time-dependent Schrödinger equation. H bar, of course, is just the reduced Planck constant, h divided by 2 pi. More importantly, if this potential over here is independent of time, that will allow us to factor the wave function itself. That time-dependent wave function can be factored as a spatial component times a temporal component. And this spatial component, right, the spatial part of the wave function, it describes the stationary states of the system. Why do we say it describes the stationary states of the system? Well, let's do this, okay? Let's take that generalized time-dependent Schrödinger equation, right, and say we've got a potential that doesn't vary with time, therefore we can factor it, as we've seen here, into a spatial and a time-dependent part. What is this time-dependent part? Well, it turns out it simply is an exponential function, exponential of energy times time divided by I times h bar. So it looks like this temporal part looks like a sinusoidally oscillating wave with an angular frequency omega, or a total energy, which are both given by that relationship E is equal to h bar omega. And the time-dependent wave function, well, it just looks like the spatial part times this simple exponential. But we know that it's the square of the wave function, the absolute square of the wave function, that gives us the probability distribution. So what happens if we take the absolute square of the time-dependent wave function? So to take that, we've got to take the complex conjugate, that is all i's go to minus I, you got to change the sign on all the imaginary terms. We do that and we find that the absolute square of the time-dependent wave function is equal to the absolute square of the time-independent wave function. So that's why we call them the stationary states. Psi of x, the probability distributions that you get from psi of x are not time-dependent. Therefore, they describe stationary states of the system. And therefore, we can also write a time-independent Schrödinger equation, that is minus h bar over 2m, second derivative with respect to x, plus the potential times the wave function is equal to the energy times our wave function. The wave function here, psi of x, in this case, that is a complete description of the system. The wave function is found by solving this time-independent Schrödinger equation. The correct wave function requires the correct Hamiltonian. It's not easy to develop both of those non-trivial exercise. Therefore, the development of approximate methods will be critical in our further investigations of quantum chemistry.